Okay, well, thanks for the introduction, Chris. So, just to say a little bit about myself, then I've been at National Physical Laboratory now for coming on 24 years, so straight from university to NPL. I did my PhD through Warwick University whilst I was at NPL, and I now hold visiting professorships at Loughborough University in the centre of England, Harbin Institute of Technology in China, and hopefully soon one in Sweden too, in Halmstad. So, and I've pretty much for the last 24 years concentrated on surface metrology, although we're now looking at other aspects of that, which I'll talk about at the end of the talk. So today I'm going to talk about how we calibrate instruments. So now, at first sight, that might seem like a slightly boring topic, although we're going to investigate exactly how these instruments work. So what are we doing when we're measuring surface topography? There's a lot of stuff still to be done. Many people think that the field of calibrating instruments for surface topography was done 100 years ago. Well, it certainly wasn't. And there's still a lot to do, especially for the optical instruments. So, we're going to cover some hopefully new ground today, and we're going to leave some questions open as well. So first of all, I'll just tell you a little bit about where I work. The National Physical Laboratory is the UK's standards lab, so that's the equivalent in the UK of your NIST here, National Institute of Standards and Technology in Gaithersburg. So we're founded in around 1900. We were just beaten by the Germans, so we were the second national lab set up. We're one of the world leading. We tend to say that the three world leading labs are NIST, NPL, and PTB in Germany. So they're really the top three. We've got about 450, more like, actually that's pushing up to 600 now. 600 specialists in measurement science. We have state-of-the-art laboratories, which were built over the last 10 years or so. We have very, very nice lab space. We're at the heart of what's called the National Measurement System, which is about 65% of our funding comes from the government, and the rest we have to go out there and earn. We're what's called a GOCO. So you probably have similar in the States, which is government-owned, contractor-operated, which means that we are owned by the government, but we're operated by a third-party company, and that company is Serco. However, we've just heard from the UK government that from March 2014, we will no longer be run by Serco. We are going academic. So we're going to be run by an academic consortium of some kind, which I think will be quite a surprise to your guys at NIST, etc. It's quite a surprise to us, although it's a pleasant surprise because we're going to increase by maybe up to 200 people. The size of the area is going to increase. We've just been given £25 million to build a new advanced metrology lab, and we're going to be able to have PhDs on site, etc., etc. So it's happy days at the moment at NPL, and that's all because the UK government, in its infinite wisdom, has decided that we're in such a financial problem that we need to start making things. And I think many of us could have told them that a few years ago, but that's what we're going to do now. So they're pumping loads of money into manufacturing, which I believe you're doing here in the States as well. Advanced manufacturing, of course. We can't compete with our Asian colleagues. So what do we do at NPL? We develop and disseminate the UK's measurement standards, so that's exactly the same as NIST, and we ensure they're internationally accepted. We also do multidisciplinary R&D, so we don't just do the standards work, we don't just do the traceability work, we do the R&D as well if it relates to measurement science, and where we have quite a large position in the UK for promoting science as well. So we get out to all the science fairs, we talk to kids, we talk to graduates, etc., about science and a career in science. So what am I going to talk about today? So I'll talk about some basic definitions. So we'll get right back to the basics and make sure that we got our terminology correct. I'll then talk about the traceability route for surface topography, how we define that. The current ISO landscape, which Chris knows all about, of course. What we call the metrological characteristics, which are very important for understanding our approach to calibration. So we need to go over those in some depth. I'll then come on to linear theory and this approach to calibration that we've started to adopt now. And the maths doesn't get too tough because it's all nice and linear. But we'll talk about where that theory falls down and where it's useful. And then I'll talk about some future work, and also I'm going to very briefly at the end, if we have time, just talk about some other areas that we work on in the same, which is related to surface metrology. So an important concept, really at the heart of what we do at National Measurement Institutes is this concept of traceability. Now, can I just ask, who's not heard of traceability? Be honest, if you've not come across traceability before. You've never heard of traceability? Okay. So that's one person. So we'll go through traceability in a simple case. I'll take the case of a pair of vernier calipers, and I'm trying to measure this part. I'm making these on a production line, and I want to assure the quality of this part, so I need to measure this dimension. So how do I do that? The measurement, I measure that with a pair of calipers maybe, and I take the reading from the calipers, or I take the reading from the digital output from the caliper, or whatever. But how do I know that's correct? How do I know that I'm getting the right answer there? Well, to do that, I need to check that. I need to compare my calibers to something more accurate. So, and that process is a process that's called calibration. There is another part to calibration which I'll come on to in a second. So I would check that with something more accurate. But then, of course, the question becomes sort of never-ending. How do I know the thing I've just checked it against is more accurate? How do I know that that thing that calibrated that is more accurate? And where does it stop? Well, the buck stops at what we call the meter. We have this thing which we define as the meter. And the meter is not a lump of something which is kept in Paris. It's not a lump of metal because that expands and changes with its chemical constitution, so it changes. So the meter is defined as the length of the path travelled by light in 1/c of a second, where c is the speed of light in a vacuum. Okay, so that's how we define the meter. And it's a very nice definition. It's philosophically pleasing definition because it relies on a constant of nature. Okay, so it's something that we would say that isn't varying. Einstein told us doesn't vary. Quantum mechanics says it varies a tiny bit, but it's not a lot. And it's nothing for people who are measuring these parts to worry about. So we have a definition of length which is defined in terms of universal, unvarying constants. So that's where the buck stops. That's where our calibration process stops. Now we have to have some kind of experimental realization of that unit. And that experimental realization of that unit is a laser. And if we have the simple equation that we know that the speed of light, c, equals the frequency of the light times the wavelength, oops, I'm doing that upside down, times the wavelength, then we know this is a constant. If we can have one of these fixed, and in the case of a frequency stabilized laser, so we stabilize the frequency by looking at some kind of atomic transition or something like that, then we can use that as a measure of length. Okay, that's our ruler. We can do it the other way around as well. We can fix the frequency and fix the wavelength and use the frequency using a time-based method. But this is what we tend to use. So we have this frequency stabilized laser, and that's our realization of the definition of the meter. Okay, so how do we get from that though? So we've got meter up here, then we've got laser, frequency stabilized laser, so we'll call that the frequency stabilized laser. We would then check another laser using that one, because that's an expensive one that's kept at a national lab, and this one we would probably use in what's called an interferometer. Have you all come across interferometers before? There's a few nods. So interferometers, I will talk a little bit about interferometers later, but let's just say an interferometer is something that uses a light source and it measures length in terms of wavelengths of light. So if I know what the wavelength of my laser source in my interferometer is, I can measure length which is traceable right back up to that definition of that meter. Okay, and I've used that interferometer to measure gauge blocks, slip gauges that you've all seen. Those slip gauges I could then measure using a mechanical comparator, or I could in fact check the slip gauge with my vernier caliper, and that's it. Hey presto, I get to the mobile that I'm trying to measure out in industry. Okay, so we've got an unbroken chain of comparisons back to that definition of the meter, and that's traceability. Okay, and all measurements in industry tend to have something like this chain here. And notice at the bottom there, this statement here, all having stated uncertainties. It is impossible to compare two measurements unless I understand about their measurement uncertainty. Yeah, it's not possible because I don't know what the value is. Okay, if I say that I've got, Chris was looking at me in such a way, I'm going to explain that in one way. So if that's my, this is here, this is x, that's my true value, something that doesn't exist, but let's just say we get as close to it as possible. This is our true value. Okay, now we're trying to measure that value. So we get 1 point here, and we get 1 point there, and we get 1 point there. Are they the same? Are they different? Can we compare them? We can't compare those because we don't know. If the uncertainties in those measurements are something like that, so we have that degree of uncertainty in the measurement, then clearly they're different. They're different answers. But if the uncertainty in the measurement is like that, it's the same answer because the measurement lies somewhere in this interval. Okay, so you cannot compare things unless you have an uncertainty. So you cannot claim traceability unless you have uncertainties. Now I'm going to have to move on a bit. I can't spend so long on each slide. So a few more terms. Calibration. Well, you can read this. This is the definition that you get out the VIM. The VIM is the vocabulary in metrology. You can download that off the internet. The latest version was 2012. And that tells us the terminology for metrology terms. But calibration is that comparison process, okay? But remember, calibration always has an uncertainty associated with it. So when I calibrate an instrument, I am ensuring that when I do measurements with it in the future, I can attach uncertainty statements to those measurements. It's why we do calibration, okay? It's not just done to give me the right answer, it's giving me the right answer with the associated uncertainties. Okay, so that's calibration. Then we have verification. Many people get these two mixed up. Verification is the ability to say that the instrument does what it says on the tin. So it allows me to look at the specification of the instrument, maybe the manufacturer's specification, and say, yes, it seems to do what that specification implies. It has nothing to say about measurement uncertainty. Okay, so calibration and verification are not the same. Often if you calibrate an instrument, you can also verify it, but that's not always the case. Adjustment, or sometimes called self-calibration, erroneously called self-calibration. Adjustment is when I adjust my measuring instrument. So I may be measuring the calipers, and I may put in a certain gauge block, give that a value, and then I adjust the output of the caliper to give me the appropriate result. That's adjustment. Again, it doesn't say anything about uncertainties, etc. Although I may use a calibrated value to do that, which would have a certain certainty associated with it. So there's just some terms which I'll throw around during the talk. So what are we talking about today? Well, we're talking about surface texture, surface topography, and who needs it? Well, I challenge you to come up with any industry that doesn't require some kind of control over its surface structure, over the surfaces. And that can be in manufacturing industry, and there's examples here of car body parts, structure of these lighter housings, orthopedic joints, camera lenses, solar arrays, cam and crankshafts, microelectronics, and the list goes on and on and on, of all the industries that try to understand where the surface. What I'm not going to talk about today, which I know is an area which you're very interested in, is these days people try to engineer surfaces. So rather than just either trying to make for example, if we have two bearing surfaces, rather than trying to make those two perfectly flat, or just using the machining marks that I've got from the manufacturing process to try and get the bearing correct between those two surfaces, you might impart a deterministic structure. So you might put a series of circular holes or a series of square grids or some other deterministic pattern which affects how the surfaces operate. And if you look at nature, that's exactly how nature does it. So shark skins, beetles' skeletons, lotus leaves and things like that. They all engineer the topography to try and affect the function of a part. So that's where industry's going these days, is more and more control over the structure to affect the function. Okay, so the instruments we're going to talk about today are the classic instruments that we've used for many years now to measure surface topography, and that's the contact stylus instrument. So that's where we drag a usually diamond-tipped stylus across the surface, and we look at the up and down motion of that stylus as it crosses the surface. And then if we want to build up a 3D map, we might scan a series of X profiles and build up what's called an areal map of the surface. And then we've got the optical instruments, and that's a confocal microscope. I'm not going to go into the operation details. That's what's called a coherent scanning interferometer, or most people call them a white light interferometer or a vertical scanning interferometer, and that's a focus variation instrument. So all of these optical instruments scan in the Z through the point of focus and therefore build up a 3D map of the surface. And now a couple of things to note about the difference between the two is that the stylus I understand. Okay, I can do the maths for what happens when I roll a ball across the surface. I understand that. What I'm actually saying there is that I understand the spatial frequency response of the instrument. I understand how it responds to different wavelengths and heights. Okay, that's what I'm saying there. I'm not so good at solving Maxwell's equations, okay, which are very, very complicated and highly nonlinear. So therefore, it's not so easy to understand what's going on when I bounce light off a surface. But we're going to make an attempt to understand that in the talk, or at least understand it from its linear perspective. Also, the other problem with the stylus instruments is that I can take maybe a minute to take a profile of 1,000 points with the stylus, but if I want 1,000 points because I want a square grid, I'm into hours of measurement time. It's 1,000 minutes. Okay, so stylus is incredibly slow. These instruments, okay, the confocal scanning, I've still got to scan, but because it's optical, first of all, the dynamics change because I haven't got to have physical contact with the surface, and secondly, with an instrument like this, I can actually take an aerial map of the surface within the field of view. So it's a full field method, and it actually snapshots an aerial measurement almost. If we didn't have to do the Z scan, it would be instantaneously. There are instruments that can do that. Okay, so that's the instruments we're talking about. So what about this traceability route for these systems? Well, for aerial measurements, we're only just doing this. We only have these such instruments in PTB and MPL at the moment, and NIST use a different, a little slightly more tortuous route, but they're thinking of building one of these pretty soon. This is a contact stylus instrument. Now this is going to sit at the top of this traceability chain. So this is here. Okay, we're going to put in here a primary instrument. That primary instrument, as you can see here, so we have the definition of the meter, we have the primary iodine stabilised laser, we have the interferometers, which are then used on primary instruments. So on this instrument, it's contact stylus instrument, it contacts the surface being measured, and then I use interferometers to tell me the motion of that stylus. So I have 3 interferometers in the XY plane, so it gives me the XY and the rotation, and I have an interferometer in this axis as well, which tells me the up and down motion of the stylus. So I understand where that stylus is going traceably. Okay, now of course it's very slow, it's incredibly difficult to use, but it's a primary instrument. It has to be in a very good environment, but we have that environment. And it's only used on a very rare basis to calibrate other instruments down the traceability chain, which we would then use for customer work and for looking at engineered parts. So this is a classic example of a priceless instrument, really, which you'd find in a National Measurement Institute. This is what we're there for, to build these systems, which are then used to calibrate other systems out in industry. Okay, so this would be used to measure structures, surfaces, which we then use to calibrate other instruments. So that's the primary instrument. But what else do we need to get us that traceability route? Well, so we need calibrated, what we call areal physical measurement standards. And I'm just going to call those artifacts. I might call them calibration artifacts. I might just call them standards sometimes. But the VIM term is a physical measurement standard. So we have those. We need things that we measure on that primary instrument that you can take to your instrument to verify or even calibrate your instrument. Okay, so that's what we are. We're going to talk about those. We need software measurement standards. So we've got some pretty complicated software. I mean, for example, Chris has developed software for doing scale-based analysis. How do you verify that software? Well, and there's filtering techniques, all sorts. So you need, in some cases, you need this reference software that you can compare to. And we only have that in the case of the field parameters. We're doing it for feature parameters. We need to do it for the fractal-based parameters and things like that as well. So this is ongoing work. I'm not going to talk about this today. It's maybe not so interesting for a talk. We need methods for calculating uncertainties associated with the instruments. That's still work in progress because it's very complicated. So where are we at the moment in the ISO standards? Well, we've published a few standards. We've published, they're all called, all the aerial standards are ISO 25178 part something. Part 1 is on the drawing specifications. That's not published yet. Part 2 is on the parameters. Part 3 is on the specification operators, or the filter settings, basically. That's now published. Part 601 and 701 cover stylus instruments, and Part 602 covers a particular type of chromatic confocal instrument. I would argue 602 was probably published ahead of its time, should not have been published. Then there are going to be Part 602, 603, 604, 605, 606, 607, 60, the list goes on and on and on. And each of those are because we decided in the standards committee that we would have a separate standard for each instrument. Now, as Chris knows well, I fundamentally disagree with that philosophy and fought it very hard for a number of years, and I lost. Well, I had to compromise. We are now stopping at 607. We're not going to introduce any more, and then hopefully when we've developed one standard which will cover all instruments, so one standard which tells you how to calibrate aerial instruments in general, and I'll come on to how we do that in a minute, then hopefully we'll go back and take out all the unnecessary parts of these standards, because industry is not going to like having all those standards. I don't think they're going to want that at all. They want one standard they can refer to. So Part 600 will cover the metrological characteristics of the instruments, which I'm coming on to. Part 700 will cover the calibration. At the moment, PTB and Polytech are writing the drafts of those, but we will be helping them. Then we'll withdraw, then we withdraw and review the 60X series. Well, we won't necessarily withdraw them, but and yes, I've compromised there. So how do we calibrate aerial instruments? It's quite a complicated instrument. Something that measures a surface is complicated. It's far more complicated than just measuring a length or a temperature, because it's a complex variable. Well, we define these things which we call metrological characteristics. Now, what we're trying to do here is solve a minimization problem. So we want to know what are the minimum amount of parameters I need to know about that instrument to allow me to then measure things with that instrument and calculate uncertainties. Okay? So what are the minimum things I need to know? Now, this is as opposed to what are called influence factors. So I can list hundreds of influence factors for a given instrument, all the different things that can influence that measurement possibly. But it's no good saying to industry, you've got to determine every single one of those influence factors. And you've got to quantify every single one of those influence factors. So what we want to do is we want to lump those together into the minimum amount of things you can experimentally determine about that instrument that tells you everything about that instrument. Okay? Now you're always going to get an uncertainty budget which is a little bit higher than if you measured all the separate parts. But that's okay. Conservatism in this game is good. Okay, so people at the National Measurement Institutes, they may measure all the influence factors, and indeed we do. But we can't expect industry to do that. It just ain't going to happen. So we're going to try and define the minimum amount of metrological characteristics you can define about an instrument to allow you to say it's calibrated. And those we define as the those we define as the noise of the instrument. Now that's the static noise. So that's the noise of the instrument if it just sat there and didn't measure anything. Okay? Now that's a very controversial point, the noise, and I will cover it in some detail. The reason it's controversial is because actually the noise will vary depending on the thing you're measuring. So you'll get a different noise when you measure that to when you measure it like that, for example. But we'll come on to that. We don't think noise should be a metrological characteristic, but I'm not going to go into that. Residual flatness is all surface topography measuring instruments compare to a flatness datum or a form datum. There are some instruments that compare to a sphere, for example, and they compare to some kind of form datum. So we need to understand what that form datum is, because that's, if we can't get everything will be compared to that. And for example, with the Stylus instrument, it will be the guideways on the Stylus instrument. For a interferometer, it will be the reference mirror. For a confocal, it will be the confocal plane, the focal plane. Sorry. So that's the residual flatness. We need to understand that, and I'll cover that in some detail. The straightness, the squareness, and the linearity of the scales, i.e., how good is the instrument in X, Y, and Z? So how good is it at measuring length in X, Y, and Z? Okay. And then we come on to this thing called resolution, and I'm going to talk a little bit about resolution in a minute, and we define that by what's called the lateral period limit. And hopefully, well, no, definitely now, these will be common across all instruments. These terms will be common across all instruments. So it doesn't matter whether it's a stylus, a confocal, a focus variation, whatever it is, then we can define these. You can experimentally determine those, and then you can calibrate your instrument, i.e. go on and measure things with and understand what the uncertainties are. And we also need the software measurement standards, and I spoke about that. So resolution in 25178, what do we mean by resolution? So the resolution of an instrument, and please don't let anyone tell you any differently, because some people do, resolution is defined in terms of how well I can tell that I have two things. Okay? It's nothing to do with, for example, can I see this? It's to do with whether I can see two of those.
In the first case, don't you have two things when you have two edges on
Unless you define that as, yeah, okay, you can define that as 2 points there, but that's a bit controversial, but yeah, I see what you mean. In fact, the example I give will be something like that in a minute. But what I mean is that resolution is not necessarily, if we have these, it isn't this distance here, okay, which a lot of people define it as. So resolution, it will be that distance in between the two centres of those. But the point is that when I use any instrument, any measuring instrument that images, i.e. it tries to build up an image of a surface, and the Stylus instrument images, even though it rolls a ball across the surface. So if I'm trying to measure that, I then have some kind of imaging system, whatever that is, I want that to be the output. Okay, so if I measure an infinitely thin point, this thing here, a delta function in mathematics, and I want a delta function out. Okay, but I don't get that. I get a blob, which looks like that, which has a certain width here and a certain shape. And that blob, in the case of a stylus, it will be because of the stylus shape. In the case of an optical instrument, it will be because of the finite resolution of the optical instrument, because it can't see certain spatial frequencies on the surface because of near field effects on the aperture. So that's resolution. The fact is that when I measure two of those delta functions, I get two blobs. Look like that. Okay, so resolution is when those blobs merge. I can't say that I've got two lines. I can't tell that I have two lines. At that point, that's the point of the, we define the resolution. There's various ways to define that. You can define it in terms of the gradient of this curve and things like that, but it doesn't matter about the definitions. So that's what we mean by resolution in in an imaging sense. Okay, so, and we can define that quite easily. There's Lord Rayleigh came up with a method for stating that's the one that most people use, or Sparrow, and the Sparrow limit is just a little bit smaller than the Rayleigh, so it's the one that all the optical instruments use, or instrument manufacturers use. They all quote Sparrow, and Abbe is another one, but it depends on the source that you use. But that's no good really. If I've got a 3D instrument, so if I'm measuring that, okay, I might have the ability to resolve this feature. Okay, I might be able to say that that's there, but I measure that as the height. Will we say that's resolved or not? It is resolved, is the answer. Yes, it is resolved. But is it any use for me if I'm trying to measure 3D structure on a surface? Okay, for a structure like this, it's obvious. But if I've got a random surface like this, you know, this sort of thing's going on all the time, can I safely say I can measure that surface or not? So we need to define something which captures that, the ability for the instrument to resolve, but also to get the height right. Okay, and we have this thing which you may have heard of called a transfer function. Transfer function simply says transfer function tells me the spatial frequency response of my instrument, and if we break any surface, you can break any surface down into a whole bunch of sinusoids. Okay, and Fourier told us that we can do that. So any surface can be mathematically broken down into a bunch of sinusoids. So, and what our instrument will do, it will allow some sinusoids through, no problem. It will block some sinusoids because of the finite resolution of the instrument or because of the range of the instrument, and it will partially let some through, i.e. it will affect the amplitude. Now, we are going to assume just for a second that our instrument response is linear, which means it doesn't affect the frequency of the sinusoids that are going through. So it's going to block some, let some through nicely, and affect some as they go through. How it does that is the transfer function of the instrument. That tells me about that blob, and it tells me how the instrument will respond in this respect. So in the case of the, if it's measuring like that, and it's let that through, it's let those spatial frequencies through. If it's measuring like that, then it's affected them. If it just doesn't see anything at all, it hasn't let those spatial frequencies through. So that's how we define. Now, so we get this function, this transfer function, which lets some spatial frequencies through and blocks others. Okay, so these are all getting blocked. 0% of it's getting through, and here 100% of it's getting through. Okay, we're just going to define now this thing called the lateral period limit, and that's the point where it's the spatial frequency where 50% of a sine wave gets through. Bang, and there it is. Now, it turns out that if you've got if you look at an instrument that has, say, a red laser source, and it has a numerical aperture of, I don't know, 0.55 or something like that, then you're going to get a resolution of about 500 nanometers. Okay, so you can see lines at 500 nanometers spaced. But if you calculate its lateral period limit, it comes out about 1.2 microns or something like that. So I would argue you should not be measuring surface topography below wavelengths of about 1.2 microns or something like that. So you shouldn't use the instrument at its Rayleigh resolution. Not unless you're only going to be looking at flat structures for example, the semiconductor industry. It's useful, yes, but so we're trying to get instrument manufacturers to start quoting this lateral period limit. And I'll talk a little bit more about that. I'll talk about a method to actually calculate or to determine that lateral period limit in a bit. And as I say, I'll talk about that later. Now, just to, I need to make a little distinction between, there's two types of transfer functions. So when we have an optical instrument, let's say we've got an interferometer, so we're looking at the phase, we're looking at the difference in phase on the surface. Okay, the signal is effectively phase differences that we're looking at. If I determine the transfer function from that phase information, that's what's called an optical transfer function. However, what most of you have got access to in your software is height data. So someone in that instrument has calculated from the phase, they've calculated height. In the case of a confocal, they've calculated the intensity data into, turned it into height data. That process, so going from what the instrument gives you to the height, is nonlinear. So it scrambles some spatial frequency content. It's a nonlinear process. And that we call the height data, the transfer function you get from the height data, the instrument transfer function. But really what you want to get to is the optical transfer function. The unfortunate business is that in most instruments you don't have that capability. So we define in the standard, in fact, we define this lateral period limit on the instrument transfer function. So you've done some scrambling there. You can't go backwards. You can't reconstruct the surface from that data because you can lose information when you do it. Well, you can over very small slopes. And watch for these new definitions of resolution which pop up. Even in places like Nature Photonics, I've seen new definitions of resolution. One of our very reputable instrument manufacturers here in the States, actually, has now got instruments, or they're saying our instruments using super resolution. I'll just tell you one little story, or one little fact about super resolution, and that is that if you're just using normal imaging, you're not using any nonlinear effects such as fluorescence and things like that, then the only way you can get super resolution is if you have a priori information or you understand magic. Okay, so don't let anyone tell you that it's super resolution unless they're using a priori information, because you can't do it. You're breaking the laws of physics, and we don't like that. So we've defined these metrological characteristics. We know what those are, and now we need a bunch of artifacts to determine those metrological characteristics that everyone can use in industry. So that's what we've built. Or what we've developed at MPL. We developed this, what we call our areal bento box. For those of you who don't know, a bento box in Japan is a Japanese lunchbox with some different compartments with lovely little nice things in each of the different compartments, and the Japanese love them as their lunch boxes. Now what we've done is we've built these various artifacts, which I'll show you in a minute. But what more importantly is that we've used fairly complicated machining processes to make these artifacts, but we then use electroforming, nickel electroforming, which is cheap to produce replicas which people can use. So even calibrated, we intend to sell this entire box for less than $3,000. And that, you couldn't buy one of these for $3,000, these artifacts. Now we're going to sell the whole box. So all you need to outlay is $3,000, and your instrument, you can say it's ISO calibrated effectively. So that's where we really think we can make a difference. You'd be into tens of thousands of dollars if you bought all the artifacts separately and had one calibrated by NIST and one by PTB, etc., etc. And we've also developed these bunch of good practice guides which you can use with those artifacts, which tell you how to calibrate the metrological characteristics of your instruments. These are literally weeks away from being commercial. We're just at the very last step at the moment. I really wanted to bring a box along and guide along, but I was told I wasn't allowed just yet by the commercial guys. So here's what you get in the box. You get step heights, which allow you to calibrate the z-axis, cross gratings, which allow you to calibrate the x, y. You get this star pattern, which allows you to do the lateral period limit, which I'll come on to in a minute. An optical flat, and these irregular artifacts are in fact what we use for verification. I'm not going to go into these today, so you would just put these under to make sure the instrument seems to be doing what it should be doing, and you would determine a parameter with these. So measurement noise. So the measurement noise is a combination of the internal noise of the instrument and also the environment as well that you're operating in. So if you're operating in a noisy environment, you've got lots of seismic vibration, thermal problems, etc., you're going to have a higher noise level. So we needed to come up with a test which allows us to isolate the measurement noise from the intrinsic roughness or any flatness deviation of the instrument. Now, just a little aside, but a bit of my personal opinion here. I don't think that we've come up with methods for doing this, for determining all these parameters, but I don't think that I should be standardising those. I think it's up to you how you determine noise, flatness, linearity, etc., etc. I think we should define the metrological characteristics. Here's the next battle coming up, Chris. We should define the metrological characteristics and leave it at that. We can have good practice guides, we can have textbooks, we can have educational seminars on how to calibrate instruments, according to my opinions, but we shouldn't standardise those. It's up to you to do it how you think is best for your particular instrument. And I'll show you, when we try to come up with methods that are across the board for all instruments, we run into problems. But here's the methods that we will put forward. Of course, we would love these to be standardised, because then we'll sell artefacts. That's not the point. From a philosophical point of view, I don't think you should be standardising how to calibrate an instrument. Only the things that you need to measure to be able to calibrate that instrument. But that's still to be debated, and we have a big fight with the Germans on this. Okay, so how do we do? We have two methods for determining the noise. I don't want to go into too much detail. It's pretty simple stuff, to be honest. The subtraction technique just takes two repeated measurements in fast succession, and then the measured topographies are extracted from each other, and the measurement noise. SQ, by the way, is, have you heard of RA? You've all heard of RA. Okay, and then you've heard of RQ, which is the root mean square version of RA. SQ is the areal, the three-dimensional version of that. Okay, so SQ noise can be estimated by the SQ of the resulting topography divided by root 2. The reason you divide by root 2 is because you've taken two measurements. So you're working out the degrees of freedom effectively. So it's a very simple test, that one. Then there's a method which the Germans put forward in the VDI guide, which is a German de facto standard. And this uses an averaging technique which takes repeated measurements at the same position and the same sample, and it uses that average value instead of using the subtracted value. And you get the same results with the two methods if you've got a nice stochastic noise or if you've got a random noise, it's white noise. If you've got non-stationary noise, or you've got problems with the noise because there's drifting and things like that, or it's not staying the same, or you've got some bursts in it or something like that, then these techniques really don't apply very well. You need to think of other techniques. And you can use this equation, a fairly simple equation, to calculate the noise. And here's an example. This is an example with a coherent scanning interferometer. So this is a white light interferometer. And you can see here the averaging technique. It's slowly getting better and better as I do more averages. And what we look for is, we look for the average to tail off. And at that point where it tails off, we say, OK, we don't really need to take any more averages. So it's something you can determine about your instrument and its environment. OK?
So this is the average of the heights?
Yes. So this is a profile taken without moving.
Right.
Okay, so this is just measuring a flat, basically. Of course, with a coherent scanning interferometer, it has to scan in Z, so it can't not move. It has to move. So the noise is a combination of the motion of the Z as well. With a stylus, you would just sit it there. Sit it on a flat and take the measurement. But you can't physically do that with a coherent scanning interferometer. So static noise is, whether it applies at all, I really don't know. But that's what we're being told in ISO standards. So this is the sort of noise level you get. Now notice this is a high-end coherent scanning interferometer. This is a very good lab, very high level of vibration isolation, very good thermal control, good environment, no noise, air current fluctuations, and we'll get. Sorry.
The phone didn't ring.
The phone didn't ring. No. Maybe then. Something like that. I don't know. And you're getting a level here which is about, I don't know, the RMS on that's got to be a 0.25, 0.3, something like that. And that's pretty good, okay? 0.3 nanometers, that is. So these instruments are going to be limited down to about 0.2 anyway, because that's going to be the pixel noise of the camera. You will see on instrument specifications, people quoting, and there's one company which is worse than others, I'm not going to say who it is, noise levels of 0.01 angstroms, which is 0.001 nanometer picometer. It's just absolute nonsense. But that's what they quote. What have they done? They've probably averaged 10,000 times, something like that. So how they think that is meaningful to a user, I have no idea. But it's not meaningful to a user. It sells instruments in China, quite simply. So that's what they do. Specification wars. Here you can see the example. So that's the average method, and that's the subtraction method, and these are the sort of values you get for two different apertures here. 4 nanometers, 5 nanometers in that case, 1.5, 1.4 there. So they give pretty close.
I'm sorry.
Back to there?
Interrupting. Maybe everybody else understands. On the earlier slide, you're subtracting the root mean square values.
Yeah.
So you take the
No. So you're taking a measurement, you're just subtracting that, and then you take the root mean square of that.
You're taking a measurement,
So
and you take the root mean square.
So the measured topographies are subtracted from each other, and the measurement noise can be estimated by the SQ of the resulting topography.
Okay.
Yeah. Does that make sense?
So if I do 2, that's obvious.
Yeah.
I'm subtracting the heights at the same position.
Yes.
Or what I hope to be the same position.
Yeah.
Because things probably move.
Maybe. Yeah.
So then in the next one now, so the Germans are taking the mean.
So the measured topographies are averaged, and then they find the SQ. So they're not subtracting here, they're just averaging. They should be, as I say, in statistical sense, it's the same, really.
But they're not subtracting the heights from each other as in the previous example. They're subtracting the SQs from each other.
They're not subtracting anything. They're averaging SQs.
I see SQ minus
Uh,
the equation.
yeah, okay, yeah,
This is
minus the mean. So this is the root mean square.
That's
It's the standard deviation.
of the SQs,
Yes,
not the heights. of
that's
the
right.
location.
That's right, yeah.
And the previous one used the heights of the location.
Yes.
Right.
Yeah,
This one is going to the SQ.
yes,
Okay.
yeah. Yeah. If you do the sort of, the summation equations, etc., they should be pretty much the same. If it's white noise. Yeah.
We've been doing this for years and reported on it.
Yeah.
And I'm just trying to get the nuances of the way you've done it so we can compare to what we've done or what they've done. The bank, all right, I think I get it now.
Okay.
And this series that you're showing here is.
So this is just the averaging effect. The average one is left. So that's showing the different, so this is the different numbers of averaging. And this is the subtraction technique.
And what are you subtracting?
So this is the subtraction technique where we subtract the two topographies, one after each other in quick succession.
With the one on the left, then you've taken 4 measurements, A through T.
Yeah.
Or each one is this.
So that's a running average.
Oh, it's a running average.
Yeah.
So you've taken 5 measurements. The
Yeah.
first one is average nothing. The second one is the average.
Yeah, I think actually it's not 5. One is 2, one is 4, one is 8, one is 16.
Okay.
I should put that on there.
Okay. So the last one is an average of 16.
16, yeah.
The
Yeah.
first one is average nothing.
Of 2.
Of 2.
Yeah. Okay. I'm not used to such scrutiny. Right. Right. So this is the results for an imaging confocal microscope. Okay, so this is the same instrument as you have, in fact, the LEXT system. And there again, you can see the average technique on the left, and you can clearly see things going on in here. Okay, it's not random noise. And here we're comparing to the subtraction technique. And again, I think the results come out at, no, it doesn't give the results here. The results are, your noise floor is a few nanometers, something like that. So, people that are quoting SQs of nanometers and so with a confocal they're working in the noise, basically.
Excuse me, is this the same sample that you measure with interferometry?
Yes. Exactly.
So with interferometry, you get in 1/10, 0.25 nanometers variation.
About a tenth, yeah.
Confocal is
yeah.
times that.
About that,
so
yeah.
Which one is more? Which one do you believe in?
It's not that I believe one more than the other. We're not trying to get to this. Is the traceability of this is we're looking at the base noise level of the instrument. The base noise level of the instrument. This is not the surface. This is the noise level. We subtracted the effect of the surface. That's what we're trying to do. So you're not comparing against a calibrated flat here. There's all sorts of reasons why you can't do that. Well, you can't do it easily. So when you've got the flat, most people will calibrate that flat using a piezo interferometer or something like that. It's no use to you whatsoever in this case. Because a piezo interferometer, the chances are the spacing between the points in a piezo interferometer could be 0.5 millimeter. Well, the field of view is less than 0.5 millimeter here. So the spatial frequency range of the calibration is nothing to do with the actual measurement. So measuring, having a calibrated flat doesn't help us here unless we can calibrate that flat using a calibrated technique here. And we just can't do that. Well, we can do it. We can measure with our primary instrument, and we have done that. But
you have to have two instruments that have the same or similar transfer functions to be able to compare them. Yeah,
sure. Yeah, or you need to be able to understand that transfer function and take a correction, which is what we're going to do later. Yeah. But yeah, well, as to which one's correct, they're both correct. They're both giving you the noise floor of the instrument. Okay. To know how to use that noise, this always gets people talking. This is the noise bit. To be able to go forward and use that value that you get in some kind of uncertainty calculation is very simple because it's just a standard deviation. So it's just the square root of that standard deviation. So you can go on and put this into your later uncertainty calculations. The flatness deviation. Okay, so this now describes the quality of the areal reference as we discussed. And it originates from the non-ideal motion of the instrument due to the guideway or because of motion errors and things like that, or because of the reference flat in an interferometer, or because of the non-ideal focal plane on a confocal instrument. So generally the measurement choice is performed on a flat. But we define, in this case, we define it the term we use instead of using the noise, the root mean square, is the SZ. And the SZ is the height from the top and bottom parts on the surface. So it's more like a linearity plot now. Okay. And again, we have two methods. Now, there are problems with the use of standard calibrated flats, which I just spoke about. And that's because of the spatial frequency response of the flat that you're comparing to. Many people compare these types of measurements and they compare them to flats that have been calibrated using piezo's or Twyman Green interferometers, and it's not a comparable, the response is completely different. For the flatness deviation, we do repeated measurements are performed at different locations, and what we're trying to do there is cancel out the effect of the flat. And again, it's difficult to say exactly how many repeats you need to do. You need to look for when it tails off. Now, we have seen with focus variation instruments that isn't tailing off after 100 measurements. Okay, so there's issues with how you do this. And we still don't understand why that is the case. They don't understand why that's going on. But in the case of a coherent scanning interferometer, or in the case of your confocal system, 10 measurements is enough. And the parameter that's assessed, the parameters that's in the ISO standards is SZ. Now, you need a good flat to be able to do this. So if you've got a flat that's got lots of spikes all over the place, or it's got scratches, then you have problems. In which case, you have to use some kind of threshold technique. So, and I know you've done some work here. So you need to remove those spikes. And here we use a very, very simple technique, which I don't want to go into too much detail here, but we can talk about this later, where we just remove anything. We take out a very, very high polynomial. Remember, we're not changing the surface here. We're just trying to threshold. So it's not a filtering technique. It's just a method to get rid of the high points. And then we take out anything that's larger than 3 times the SQ value. Okay, so we remove any spikes on the surface. Here's the results for the coherent scanning interferometer. And you can see here you've got the number of repeated measurements for 2 different apertures here. And you're getting to a value of about 2 nanometers or so, and 3 nanometers for the 50 times objective here. Okay, so that's the type of level of flatness of that reference mirror. Now, most of these interferometers have had the flatness of the reference mirror taken away from them at this point, so that's what's left. That's why it's called the residual flatness. And here for the confocal microscope, you can see again the values dropping off as we do various repeats. To work out the flatness deviation, the contribution to the uncertainty, we divide the value of the z squared by 12, and we do that because we associate with it a rectangular distribution of the uncertainties. Okay, the amplification coefficient and the linearity of the scales. What we hope to have as we move in x, y and z, we hope to see a nice straight line. But because of the deviations in the instrument, we see a curve here. To determine this, we can just use z heights. Now, one thing I will stress here is that you cannot calibrate an instrument by measuring one step height. Now, many of the instrument manufacturers for a while have said, you measure this step height, the instrument's calibrated. I mean, we've just seen the problems with noise and flatness, let alone the linearity in the x, y and z. The point is that if your instrument cannot measure z height, then it's really not a very good instrument. Okay? All instruments should be able to get a good answer to within nanometers on step heights. Okay? It's a very simple measurement that doesn't take into account a lot of the spatial frequency distribution of the instrument or response to the instrument. So you should be able to measure z heights very well. So it's not a very good way. If you want to show how good your instrument is, then show something other than just step height results. And you can just use the ISO techniques to calculate the step heights there. I'm not going to. Here we can see the results for a Stylus instrument. We've used 4 steps here. There's the different step values going up to 17 microns, or from 9 nanometers to 17 microns. And here we can look at the deviations of those, and we see that it should follow a nice straight line, but it doesn't. And that's because of the nonlinearity in the motion of the z-axis. Here, for the coherent scanning interferometer, again you can see some nonlinearity here, and also for plotting the x and y we can use these grid plates. Now with the grid plates, notice most people, and in the VDI standards they say that what you should do is calculate the what's called the PSM, the average wavelength structure. That really doesn't tell you anything about the linearity of the instrument. Okay, so if you want to calculate the linearity, you need to calculate the center points of these or an edge point of these and plot a line through that so that you get a linearity curve for the instrument. And you can calculate the squareness of that for the axes as well. And here's just some results you see for the various instruments. You can see for the XY grid there. And then we've in our good practice guides, we've given you various techniques that you can use to calculate the uncertainty associated with those scales. And I won't go into that in any detail. It's not not important for today. For the resolution, so the z-axis resolution is usually with these instruments is small compared to the contribution of uncertainty, for example, from the noise. So it's very rare that people actually determine the z-axis resolution. So we usually accept that that's within the noise value. There's multiple definitions of the lateral resolution. We've talked about this, but the one we're going to try and determine today is what we call this lateral period limit, which we spoke about over there, which is the spatial period of a sinusoidal profile at which the optical response falls by 50%. Okay. Now we can test that against a grating with a defined pitch, but there's an issue which I'm going to show you in a minute, which grating won't tell you. So the way we do it is we use a 3D star pattern, like this. So we have a star pattern where you have these are high values, these are low, high, low, high, low, high, low, high, low. Okay. Now, one way to get the resolution, the Rayleigh type of resolution, is to look at where do we stop imaging these star petals here. Okay, so you can plot a circle there, and that will give you a value for resolution. But there's a better way of doing it than that gives you more information about the transfer characteristics of the instrument. So what we do is we take the star pattern, we take an image of the star pattern, we then we extract a profile on the top surface there, we extract a profile from the bottom surface, we subtract those two, and that's what you get, which is effectively an instrument response. So that gives you a transfer function. So here what we're seeing is where the instrument is running out of resolution, and here it can't see. Probably around here the star pattern is not perfect as well, but it can't image it anyway. So this in fact, this area here is the Rayleigh criterion. That will give you the Rayleigh resolution. But the 50%, if we normalise this axis to 100%, which I do here, and then we can plot that point at 50% off that curve, and that gives us the lateral period limit. Okay. Okay, and here you can see a couple of examples. This is a coherent scanning interferometer, so white light interferometer. That's a 50 times objective over there. No, sorry, that's a 20 times objective, and that's a 50 times objective. Note that you have to have heights of very small heights for this to work. And that's because if we have large heights, then we're outside the linear range of the instrument. And what I mean by that is when I go back to the fact that we're working on the optical transfer function as opposed to the instrument transfer function, if we calculate this on the instrument transfer function, we won't get the correct result. We need to calculate it on the optical transfer function. When we're within small heights, the instrument transfer function is okay. Okay, there's a limit when we can use that instrument transfer function. So here is so this is where we've made a breakthrough, is because people have designed these before, but they've had much higher heights, or people have designed sinusoids with much higher heights. But we've got these down to 30 nanometer steps on here, so we can actually calculate from effectively the optical transfer function. Here's an example of your instrument, the Lext instrument, and here's an even better example of the Lext instrument. And this shows you why you can't use a grating to get the resolution, or why it's dangerous to use the grating. Look what's happened with this one. Here, it's turned, at this point here, it's turned this height information into valley information. It's turned the valley information into height information. So it's inverted the profile. Now you wouldn't see that if you just had a sinusoid there. It would just look like a sinusoid. But it's inverted it. Okay, so you've got a phase change in the instrument here. Now you can describe that with if you look at the transfer function of a confocal, there are zeros in it, and you can describe this, but it's not clear from just measuring a grating. So you get this information from the star patterns, and this is telling us other information about the instrument here. Very interesting information which we don't understand at this stage about the instrument. In fact, Olympus don't understand either. They get the same results now. We've given them star patterns. So is that the job complete? We can now calculate these metrological characteristics, but just with that lateral period limit, the job is not complete. We still need to get to that transfer function. Okay, and I'm going to talk about that now. Now, we haven't put this into ISO standards yet because it's still work in progress. But this is really the exciting stuff I wanted to talk about today. So we can measure the scales and the flatness contribution and things like that, and from that we can construct uncertainty budgets. But does that mean we can go on and measure any sort of rough surface? Well, the answer is no. Unfortunately, we can't yet. Because we need to understand that spatial frequency response of the instrument. So I've talked a little bit about this, that we can understand the spatial frequency response of the Stylus instrument, and it's clear that it can't measure structures like this because the wavelength structure is too small, and it doesn't matter how clever I am, I can't reconstruct that. That's lost information because it's a nonlinear effect. But now how can I determine that for a optical instrument? How can I get the equivalent of that spatial frequency response for an optical instrument? In 25178 part 3 we define this thing called the electromagnetic surface. The electromagnetic surface, I know for a fact that Paul Scott, he put in that term just to get the debate going, and lo and behold it's got all the way through to the published standards. But I don't understand what that means. I don't know what an electromagnetic surface is. And I couldn't come up with a better method. I must admit, a better term. I'm not even sure there should be a term. But is that surface, is the electromagnetic surface the same for a coherent source, an incoherent source, different polarization, etc., etc.? I don't think it is. So there's all sorts of issues with that surface. Don't worry about the last point. Now we've got to define this thing that we call an optical surface. Now it's quite easy at first sight to define the mechanical surface. It's exactly the same as the one that's in the concise Oxford Dictionary. It's the mechanical surface which stops there. But there's surface and then there's air. That's how we define the mechanical surface. It's actually philosophically more difficult to describe than that. But how do we define an optical surface? Well, we're better off defining an optical surface in terms of a refractive index gradient, not a mechanical thing. Because that's what optical instruments see. They see changes in refractive index. Okay, so I'm sort of going to describe it like that. And that's we've actually developed a model of the surface, which we call our foil model, which I'm not going to go into the details today. It's just been published in a book at the moment. But it's a way of describing the surface, which is like it's like attaching an infinite conductivity foil on the surface, and then you can describe the surface as a whole bunch of delta functions, and you can convolve that with your optical signal, and that gives you a response. But I'm not going to go into details of the foil model. So the instrument we're going to use as an example today to go through this method, I'm going to talk you through how we might get this transfer function. Okay, and we're going to use this the vertical scanning white light interferometer, or the coherent scanning interferometer. Are you all familiar with how these operate? Is it worth? Do I need to go over 1 minute on how they operate? No. You think it will be worth it? Okay, there was a no and a yes. Okay, so have you got a rubber? Okay, I've got a slot here.
No, there's one holding up the...
Oh yeah, I got it. Yeah, I've been playing with it. Of course, then there's another issue. So, just briefly, we have a light source. That light source, this is a 50%, half of the light is transmitted, half of it's bounced off this this half-mirrored surface here. And that goes to the surface we're trying to measure. And this comes to a reference surface. So what happens if this is a nice coherent source, so it's a laser source, it's monochromatic, we get the light comes back and forth, back to this point, and off we go to some kind of detector. Okay? At that point, because I get interference of the waves, which I'm not going to go into that right now, but as we see interference, if I move this mirror, what I will see at that point is the amplitude of the waves will go like that because of the interference effect. Okay, where this distance here is going to be the wavelength of the light source. I'm having problems with my lambdas today. Lambda over 2. Okay. Yeah, so that's the classic Michelson interferometer. Now, if we set that up as a full field interferometer, so we do something like this and we send that light through there and that light through there, and then we focus onto the surface and focus onto we're going to get a full field pattern. So if I've got a perfectly flat, if this is perpendicular with this, as I scan that mirror again, I see it goes dark light, dark light, dark light, dark light. If I tilt this slightly, you're going to get this series of interference fringes running across here. And again, we know these are an exact contour map of the surface where the distance between the contours is the wavelength of the light divided by 2. So if that mirrors, if this isn't flat, you'll see the contours doing something like that. Okay, so this is basic interferometry. Now I have a problem. If I have a step in this surface, so this surface actually looks like that, then I get a series of interference fringes which look like, there's the step, and then I might see them like that. Okay, all I measure in an interferometer is the fraction of that fringe. So all my steps are the length of any step I measure in an interferometer of this type equals a number of fringes plus a fraction of a fringe. Okay, but that's all I measure in an interferometer. I can't measure that. So I have a problem. I'm limited to height differences of about, it turns out, about lambda over 4. Okay, so if I have heights on a surface with a monochromatic source here, a phase stepping interferometer or something like that, I can't see heights which are height differences which are greater than about lambda over 4, because it could be n could be any value. It could be a massive step, it could be a small step. Okay, so you only measure fringe fractions. So what we do is, the clever thing is to put a non-monochromatic source, a incoherent source here, so maybe a white light source with loads of different frequencies in it. Then we send that down the interferometer, and you'll only get interference. You'll only get all the different frequencies being in phase when the path difference between here and here is equal to the path difference between here and here, or here and here, sorry, which is to say that I get the zero optical path difference in the interferometer. And what you see is, if I was to look at 1 pixel on this surface, you'd see no interference whatsoever, and then it'd start to interfere as you get sort of coloured fringes, and then you'll get a high point like that. So it's not drawn very well. There'd be some symmetry here as well. But you'd get something like that. That point there is the point of zero optical path difference in the interferometer. So now I've got the same type of resolution as this. So I've got axial resolution of a nanometer or less, but the scan range is not lambda over 4, it's the scan length of how I scan this mirror. So I scan this mirror, and at each pixel I look for that point. So that's how these instruments operate. Is that clear? It doesn't matter too much, to be honest, for the argument I'm going to go ahead and talk about. And we have this objective here. The interferometer is not set up like that. It's set up like this, where we have a little mirror inside the objective. It's called a mirror interferometer, and the reflection is off here. So we're comparing that with that. Okay? Probably more detail than necessary, but okay. Now the problem with these interferometers, and all optical instruments like these interferometers, so they all have similar effects, are that you get edge effects. And I'll show you some pictures of edge effects in a minute. They're often called bat wings. So you get, instead of measuring an edge like this, a nice edge, you tend to see something like that. Okay, it's underestimates and overestimates the heights. And that's multiple reasons for that happening, but we tend to call that a bat wing. It should only really be called bat wing in a particular coherence case, but everyone calls them bat wings for everything. Then there's ghost steps, which are misinterpreting the fringe order, sometimes called a 2 pi error. multiple material effects because of different phase changes on the surface, and the big one is multiple scattering. Now, if you've got a rough surface, that means that instead of the light bouncing off and going straight back up into the aperture, it actually does more than one reflection on the surface. That is a serious issue because all of what I'm going to talk about starts to fall down. That's what causes your measurements to be non-linear. And it's a big problem. And it's unsolved. Here's a batwing, classic batwing effect. And you can see this is a sinusoidal surface I'm measuring here. And notice it's not a resolution effect, this. It's not because I'm anywhere near the resolution. This is an 8 micron period sinusoid, about 200 nanometers amplitude. And at the points of highest slope, the instrument is giving me these batwing type effects. It's misinterpreted the fringe order. You're smiling like you've seen this sort of thing before, but yeah. So that's the type of thing you see quite commonly with a sinusoid. And notice here, it's a bit subtle this, and I need to get this redrawn, is that in fact it's not just as simple as that. In fact, it gets the heights wrong. And I'll show you a picture a bit later. I've got another one of these that shows you where it gets the heights wrong. So it's not just a slope effect going on here. There's actually a curvature effect going on as well. So anyway, that's a typical thing. Now the point is that if I've got a sinusoidal surface, I can probably cancel out those 2 pi errors. But if I've got a random surface, which can be made up of a load of sinusoids, and this type of thing's going on all the time, it's no wonder I get different answer to what my contact stylus type instrument. This sort of thing's going on all the time. But I can get rid of it. And I'll show you a way in a minute. Here's 2 pi errors. This is an optical flat measured with an instrument that has a dispersion problem. And here it's got the fringe order wrong. So this is a field-dependent effect. If I rotate the surface, this stays at the same. So it's nothing to do with the surface. There is no height there. This is an effect of the interferometer itself. Focusing is an issue. Most of the instruments I've seen are not focused. People don't focus them, or they've gone out of focus. In fact, we've had them shipped. The guy's come along and set it up, and then he's gone away and we've checked it and it's not focused. Okay? If they're not focused, here's measuring a sphere. There it's in focus, and there it's going out of focus. And at the edges you can see 2 pi errors coming in all the time because the instrument's not focused. So focusing there's nothing I can do mathematically about the focusing. It's just something you need to be aware of, and you need to make sure your instrument is focused. Here's a multiple scattering effect. Here is a V, which is outside the aperture limit of the instrument. So this instrument can't measure that V. But what happens when I do measure it is I get a load of noise, because it just can't see that. There's no information going back into the interferometer here, and then I get a multiple scattering event. So it's multiply scattered at the bottom. Instead of measuring a V, I measure an upturn V. Now, you might say, well, you're an idiot. You shouldn't have measured that using that interferometer. But what about, again, in a sort of Fourier sense, if I think of a rough surface being made up of a load of V's? This sort of thing's going on all the time. So if I've got high slopes on the surface, which I often have with a rough surface, then you're seeing this type of thing. And look how big it is. So this is an instrument. This instrument is in fact the instrument where they told us that the noise floor, or the Z resolution, is 0.01 angstroms. I've got 100 micron error with a fairly simple structure. Okay, so bear that in mind. Okay, so the technique that we've come up with uses, first of all, we calibrate the X, Y, Z. And I've told you how to do that. We can do that with the grids and the plates and the flatness tests and those sort of things. Then we have this thing that we call our point spread function measurement. And I'll come on to that. That's like checking the point. This is the new stuff. Okay, I'm going to gloss over this. Right. Here's how we set up our measurement model. Okay? And all measurement, you can set up one of these models, and they're all pretty similar. Here's the surface I'm measuring. This is the sinusoid I'm trying to measure here. And that's the foil model. I talked earlier about we set up this foil model of the surface. So we set up our foil model of that surface. Here's the instrument response. In the case of an interferometer, do you remember I showed you the blob earlier? The blob you get when you try to measure a infinitely small point. Instead of getting an infinitely small point, you get a blob. That blob is known as the point spread function of the instrument. Okay, and in this case, rather than being a blob, it's in fact a blob with lines in it, and that's because it's got phase information in there as well. So it's a blob with more lines, which is why you get a higher resolution with an interferometer than you do with a confocal microscope. So that's the response of the instrument. In there is all the information I need to know about the spatial frequency response of the instrument. That's it. It's contained within that point spread function. And that's the output. If I convolve, there's a mathematical technique for combining these two. If I convolve one with the other, the surface, the thing I'm trying to measure, with the response of the instrument, I get the output. And in this case, it's these fringes, where these would be, one of these is that high point fringe. Okay? Now, the clever thing to do, first of all, I want to do two things here. One is cleverer than the other one. First of all, I want to measure that. That will tell me the instrument response, or the response of the instrument to different spatial frequencies. Then, with a knowledge of that, I want to solve the inverse problem, go back from there to there, taking out all those horrible 2 pi errors and things that are caused by that not being perfect or being what it is. Okay, so I'll show you that going on. That's just it in the spatial frequency domain. It was that convolution in the space domain, in the spatial frequency domain. It's a multiplication. So we get this. That's just the Fourier transform of a foil. That's what's called a transfer function. Okay, so the inverse Fourier transform of a point spread function for a coherent system, for an incoherent system, is a transfer function. Okay, and don't worry about that. So now, if you're going to use these point spread functions, there's one assumption that you have to make, and that is that it's the same across the whole field of view. Otherwise, you've got to determine it. In fact, mathematically, it has to be the same across the field of view, or what's called shift invariant. It's a shift invariant property of the imaging system. Now, if your lens that's focusing down onto the surface is causing some distortion, which it will, then you're not. Your point spread function won't be the same across the field of view. So you need to do something about distortion first. So we thought, well, these instruments cost $200,000. Surely they've corrected the distortion. Well, let's see. So here we measure a grid, and this should be a whole bunch of points, because, but it's not. You get this pincushion effect. This is classic distortion. It's called Seidel distortion, or third-order distortion. Classic. And it's a third-order effect, as I say. And it's about the distortion you're getting in the XY, this is, remember, is about, in this case, 400 nanometers. So it's quite a lot. Now, if you think about that, and I'll just show you we can correct it. Once corrected, it's very simple to correct. Well, it's relatively simple to correct. We're just publishing a paper at SERP this year on this. But here's the problem. Okay, I've got this distortion. What problem does it cause me? Well, if I measure a sphere, and I've got 400 nanometers of distortion in this axis, it gives me a Z problem of 200 nanometers. So when I'm measuring high slopes using this interferometer, which they're telling us has a 0.01 angstrom resolution, etc., is very, very accurate, I've got 200 nanometers of height error on high slopes, okay, which is a big problem. So distortion was a world for us. We thought this, they would have corrected this, and a lot of them are starting to now, because they realised that no one had flagged it up before. But we have now, and we're actually working with most of the instrument manufacturers to correct this. It's very easy to correct. That's the thing. It's simple to correct. So we need to find this point spread function. That's the beast we're trying to get. One way to do that is to measure an infinitely small point. But there's problems with infinitely small points. One, they don't exist. Two, they're never infinitely small, the things that you use, because really you only need something that's smaller than the resolution, surely. Well, there's always corrections you have to make for that. Two, you don't get any light back off them, and three, you can't find them. So infinitely small points, they are used in, they use nano beads and things like that in biological confocal, but so we're not going to do that. No, we're going to use our foil model. We're going to use that equation, foil convolved with point spread function gives us the output. So we need a surface that has all the slopes, all the spatial frequencies present. And I know the guys at NIST saying, well, use a whole bunch of sinusoids. Well, I mean, you need an infinite amount of sinusoids, and all of those sinusoids have to have heights which are less than 20 nanometers so that you don't get out of the nonlinear effects, etc. So we don't. We use a sphere. And a sphere has got all the information you require. It tells you everything about how that instrument operates. So use a small sphere. Now the sphere has to be smaller than the field of view. So we are now talking about measuring spheres of about 50 microns or so diameter. So these are small spheres. Now, two things to remember about the spheres. One, they need to be highly reflective. If there's scattering coming off the spheres, you will synthesize a higher aperture. You will get the transfer function wrong. So they have to be very smooth. So it's got to be a very smooth 50 micron sphere. That's already got difficult. Secondly, we have to know the form of that, or that sphere has to be round to within the uncertainty we want to calibrate the instrument, or less than a nanometer. So where do you get spheres which are highly reflective, which are spherical to less than a nanometer? Well, you can't get them. But you can, if you're an NMI, you can have a go at measuring the sphericity and doing a correction for it. So no one can do that just yet, but we think we've worked out a way to do it. So the first place we look for spheres, we wanted to find something that's actually spherical to that level. Mercury. If you do your calculations, you calculate the sphericity at the top of the mercury sphere, mercury bead, at 50 microns, actually at 30 microns diameter, it's less than a nanometer out of sphericity. So we can use a mercury bead as a spherical reference. Now, we're not suggesting that anyone in industry does this, but I'll show you in a second. In fact, we use silica spheres from NIST. Now, these are not spherical enough, but we're going to determine their sphericity. Now, I don't want to go into details, but we're building a primary instrument to measure that sphericity. Now, if you don't mind, I'll skip over how we're going to do that. It's an optical technique. It's a combination between a confocal and an interferometer. Okay, so here's an example. This is an instrument, a high-end instrument that has been. We've removed the distortion. Okay, so first of all, this would be a lot worse if I hadn't removed the distortion. And secondly, I've focused it, so it's in good focus. So now we're measuring a 30 micron sphere, and that's the type of error you get because of the objective. So this is the error due to the transfer function of the instrument, and it's about 40 nanometers or so. So you cannot, with this instrument, say that you can measure a rough surface to anywhere near 40 nanometers. Okay? And then when we correct it by measuring the point spread function, applying that inverse calculation, we can get it down to a nanometer or so. So now that's quite exciting doing this. And we are talking to most of the instrument manufacturers because we can't get you guys doing this because you haven't got that optical transfer function information. You'd have to get to the fringes or the confocal planes in your instrument, and you haven't got that. So we're talking to the instrument manufacturers, and most of them are coming on board and saying, okay, yeah, we'll start putting this into the instruments. And here you can see it on a sinusoid. Do you remember I spoke about the curvature problem? So some people would say, well, why just don't you do a slope correction just by tilting a plane and then applying a slope correction? It's not just a slope correction. The transfer function measures curvature, so it operates on curvature as well. So here there's a 50 nanometer difference at the top and bottom of this sinusoid I'm looking at here. I haven't got the height correct because it's a curvature issue as well. So you can't just correct for slope. It has to be for transfer function. So the conclusions of this is that current coherent scanning interferometers, that should say 50 times in this case, exhibit substantial systematic errors. So we're looking at XY distortion of 50 nanometers in one case, 400 nanometers in another case. Focusing can be 50 nanometers of error, and then the problem because of the PSF is 50 nanometers for both instruments. So we've devised methods for getting rid of all of those, apart from focus, and you just got to focus it. So we can get rid of all of those methods, and I think we can now say, hand on heart, for the first time ever, that coherent scanning interferometers don't just have nanometer resolution, we can give them nanometer accuracy as well. Okay, but it's still early days. What are we doing now with this work? Well, we need to solve that 3D inverse problem we've done it for coherent scanning interferometry. We're now doing it for confocal. Confocal has a problem. When I have my, perhaps you've worked out what it is, when I have that model, foil model convolved with point spread function equals the output of the instrument, that point spread function is an amplitude point spread function. It's a complex amplitude point spread function. In the confocal case, because I work on intensity, it's the square of that. So it's the intensity point spread function. It's linear in intensity, not in field. So now the transfer function is equal to what's called the modulation transfer function, which is how the instrument responds to amplitudes or in amplitude, and plus the phase transfer function, which is how it responds to phase. Now, because of that squared term, all that phase information is gone. So I've lost an important, and it is important, and it's very important in confocal, because you saw that horrible phase effect when I showed you the star pattern. You've lost the phase information. So what we're doing at the moment, we just published a paper in J Microscopy, is we're working out methods to extract the phase from the confocal planes. And that's proved quite mathematically pretty difficult. So we're doing the phase retrieval, and we have to verify how good that is at the moment. So we're solving that for confocal, and then we're going to try it for focus variation. And the issue we have with focus variation is not that it's mathematically difficult, but the company won't tell us how the instrument works. So it's proving very difficult, that one. So then we develop a calibration method based on the transfer function. We've pretty much done that. We've still got to develop that sphere form measurement. We're actually building the interferometer at the moment to do that. Now, this is an important point. We need to investigate when these multiple reflections come in. When I see those multiple reflections, that nice equation I gave you with the foil convolved with it's gone. It becomes a nonlinear equation because I've got those multiple reflections, and it no longer has one solution. So, so it's what the initial equation I showed you is what's called a smooth surface approximation. And it works for surfaces which are not outside the aperture limit, or which it doesn't matter. But it works for, it's called Kirchhoff approximation. But for rough surfaces, when I've got high slopes present, then it becomes nonlinear, and the mathematics gets much difficult. Now we're solving that mathematical problem at the moment. Okay, the physics is there, but the mathematics is so complicated that it takes forever to solve the inverse problem. So we need to think of fast methods for solving the inverse problem, so we can apply those corrections. And of course, you're going to have some a priori information to solve that problem. You're effectively doing super resolution things here. There's all sorts of clever things when you can do that, and I'll just quickly touch upon one of those, just more for interest than anything else. Is if I've got something like that, and I've got this aperture up here like that, I think you'll agree that there's absolutely no way I can measure those vertical sidewalls. Okay? I can't measure those. Or can I? If I get some light which multiply reflects off there, and I can solve that nonlinear inverse problem, I can in fact build up measurement of that sidewall, and we've done that. Still a lot of work to do in this, but we are building up measurements of sidewalls and complex structure. I mean, in theory, you can. It's like drilling a hole in the floor and seeing a cave open up just by looking down the hole. As long as you've got some light, some photons are coming back up the aperture. Okay, so that's a tough one, and you have to know that this is roughly that shape and things like that. But we've done it. Now, interesting point here is, here I have a load of fringes and I get that data. Here I have a load of fringes and I get that data. Okay, here I have a load of fringes and I get that data. What's the resolution in this axis? Nanometer or so, maybe less. What's the resolution there? Nanometer, maybe less. I've got super resolution, very, very high level of super resolution here. Now, I don't totally understand this, but that I will appear to have a very high degree of super resolution for resolving those features there. And, please don't ask too many questions about that. And then we want to apply these methods into, not those methods, but the transfer function stuff into ISO standardization. And that's ongoing. Okay, I've got 15 minutes, so I'm just going to tell you a little bit about some other work we're doing. Those instruments can be used for measuring over very small areas to high resolution. And some other instruments can be used for measuring over large areas to low resolution. There's an example, that's a fringe projection system that's measuring to maybe 100 micron resolution there over the size of that Jaguar car door. And these instruments measure over a millimetre at most to 500 nanometres resolution. What if I want the resolution of those at the range of those? And that's what people want these days, especially for example, web-based manufacturing, where you're, by web I mean large webs. So large webs of structured surfaces for micro-optics, backlighters, projections, all sorts of, the list goes on and on and on. I think I'll show you an example here. Yeah. So here I've got a 1.5 metre long drum diamond turning machine, and I'm producing tiny micro-optics on here, which I'll then roll out, and this would be used in for plastic optic manufacture. These take maybe a couple of weeks to produce, and then they're sold as seen, because you can't confirm them. How are you going to measure that in any finite amount of time? I've seen people putting, put a tally surf on here or a stylus instrument on here or something, and it's just a ridiculous solution. So how do we measure over the large areas to such high resolution? And not only that, but if we're going to do that, it's pointless doing it slowly. Because I could put something, as I say, on there and scan the whole damn thing. It's going to take me weeks to do measurements, which is no good. I can't take double the amount of time it takes to manufacture it. Or I could put it in line, of course. So these things need to be high resolution, large area, fast. Okay, so this is a sort of new area for national measurement institutes to get into, but there's no point in us getting involved in this if we're going to produce these really slow primary instruments, because the instrument itself needs to be in line. So we're moving into the sort of inline area. We could be talking about meters to microns, even less sometimes, and then non-planar surfaces in process. So we need to start looking at. Sorry, Chris.
Is that the one that's made by Nanosystems or Nanotech Systems?
No, that's Cranfield, mate. That one. Yeah. Not Cranfield Precision. Cranfield University. So what are we doing at the moment? We've just published, well actually we're not just published, it's in my bag at the moment for reviewing. We looked at all the techniques that are available at the moment, and none of them will do this. Okay, so there's room for innovation now. We need to innovate here. We're benchmarking the types, point and line type sensors that are available at the moment, so how far can we push those? And we're also developing some large area measurement systems. And I can't go into details about those because there's patents involved and all sorts. But that's where the innovation will come in. And also, can we develop fast super resolution? So super resolution, we always bring it in and talking about trying to measure the tiniest thing possible. But how about if we use low aperture systems, so low accuracy systems, and improve the accuracy of those using super resolution type of techniques? Using a priori. Normally, if I'm manufacturing that, I know a hell of a lot of what it's supposed to look like. So I've got lots of a priori information. Let's use that. Let's use intelligent sampling routines and things like that to try and minimise the amount of data points I take, etc. So it's a very big project. This we've got a lot of people working on this. We think there's a lot of money to be made, but we have to work directly with industry here. We can't sit in our National Measurement Institute towers and develop systems here. The last thing I'll talk about is microcoordinate metrology. So this is now measuring really 3D parts. How do we measure really 3D parts? Just recently we've got a patent on a new probe, which is a micro CMM probe with a tiny 50 micron tip that uses piezoelectrics on these vibrating legs and it vibrates as it contacts the surface, which you can actually avoids the stiction to the surface that you get if you're using tiny probes. And it also, you can actually use it in a non-contact mode by coming up to the surface and saying, yeah, there's a surface there, I can feel the surface forces, and therefore not actually contacting the surface. So it acts as a 3D tapping mode of atomic force microscope. So that's something we're commercially developing with a company in the Netherlands at the moment. But where do we want to go with this type of work? So we continue to develop our probe. We've just last week, actually, 2 weeks ago, we mounted the probe onto a commercial CMM, and completely against what I thought was going to happen, it worked first time, which was amazing. But we now need to improve the software and the interface, etc. We need to measure sphere form. So when you're using a tiny sphere to measure measure CMM type structures, or in a CMM mode, then you have to take away the form of the sphere. It will act as an offset on the measurement you're doing. So again, we can use the methods we're developing for measuring the tiny spheres for the interferometry on this project as well. And the way to go really is to avoid these contact techniques and go optical. So start using those types of techniques to measure complex high aspect ratio 3D structures, and that's where we're working at the moment. Another area where we move into, I've only got one slide on this, is that where if you can't measure around these things, or you can't measure on top of them, then why not measure through them? So we've just bought one of the Nikon's first metrology system, or X-ray computed tomography system. So this allows us to measure actually the internal features of the parts we're looking at. Okay, I don't need to say that. So that's me finished. All of the information about what I'm talking about is contained in these lovely 3 books, if you want to buy them. And Chris inputted into that one and that one. So, okay, thank you.
Thank you very much. We've got the room for a few more minutes, and some of us will be joining us for lunch. If anybody else would like to join us for lunch, there's some seats at the table. Big accept.
I just had a broad question on the electromagnetic surface that you talked about there. Is that essentially something for the future, or is it really, are you able to measure it now?
So the transfer function stuff.
Yes.
For the coherent scanning interferometry, we're doing it. We've done it. So it's really tidying it up. So we're talking to the big guys, the Zygos and Brookers and people like that, to incorporate it into their instruments at the moment.
Now that's opposed to the foil or the spherical surface.
Yeah. See when you've actually, I mean, it's. There's a whole bunch of papers on the maths, etc. But what it boils down to is you measure a sphere, and then it's 3 or 4 lines of code, and you can make that correction. So it's actually very simple in practice. But we also have to we've got to get these guys. We have to show these guys that it works. Now, from my point of view, so from a purist point of view, if you can measure a sphere, you can measure anything. Because it's all there, all the information is there, but they want to see it working. They want to see a comparison with a rough surface and make sure it still works with steps and things like that. So we're doing a load of work at the moment just to prove to the unbelievers that it works. But it certainly does work. It can improve the instruments for sure.